Okay, let's do some examples related to inference for variance. So far, we've talked about there's a test statistic. We've talked about how to find the confidence interval, and we've talked about how to find some values on tables and use Excel, but it's all sort of floating details at this moment. Let's tie it all together and do some calculations. We'll first do a confidence interval calculation, and then we'll do some statistical testing, and that'll wrap it up. I mean, there's practice problems that you should do on your own as well. Okay, so we got a few examples to go through here today, right now. So we surveyed 36 air travelers, found that the standard deviation in the security lineup's wait time at the Edmonton International Airport about 4.25 minutes. Line organization improvements have reduced the standard deviation from 4.5 minutes. Calculated 99% confidence interval for the standard deviation of wait time in the security lineup after the improvements. What factors should we consider in choosing between a 90% or 99% confidence interval in our wait time? So that second question is actually a pretty important one as well. Okay. So we're going to find our confidence interval, and if we remember from before, n minus 1 s squared and squared, and then the alpha over 2 n minus 1, and then the upper bound n squared, chi squared 1 minus alpha over 2, left hand side number, which is the smaller one. And so in my really scratchy handwriting, I'm just essentially writing out how we're going to calculate this particular confidence interval. Okay. Now we got an n of 36, so we get 36 minus the 1, and the standard deviation was 4.25 minutes. Okay. Remember, it's all related to the sample. Now this 4.25 is standard deviation, so I'm going to square it because it's s squared, and I have the same denominator in both cases, so that life is a little easier that way. Okay, forget the squaring. That's easy to miss. Okay, so next step is we need the chi-squared statistics. Right, so we can go in our tables. We have our degrees of freedom of 35. So I can go down to the row with 35, and I have alpha over 2. So what did I want? I wanted a 99% confidence interval. So that means alpha 0.01, alpha over 2, 0.005, and 1 minus alpha over 2, 0.995. Okay, so a bunch of whole important areas under the curve for us. So I go across that row with 35 as the degrees of freedom. First one is 0.995, and I see 17.192. 17.192. Okay. I know that as I go from left to right here, the numbers get bigger, so therefore the first number I see is actually the denominator for the upper bound. The second number I will see is the 0.005, and that looks to be 60.275. Okay, and that's the bigger number, and that goes in the denominator of the lower bound. Okay, solve the simple mathematics, and we're all set. We're all done here. Okay. Alternatively, I could have pulled in my Excel spreadsheet, and this is always easy too, and just plugged in. I have a 0.05. Let's see, what's my first one? 0.5 with the degrees of freedom of 35, and I get 17.19182. Okay, and alternatively, I can do the same for the right-hand tail. 0.5 degrees of freedom of 35. I just punch that all in, and I get 60.27, well, 477, right? So same as what I did looking up in the tables. Whatever your comfort level is all good, right? Now, if we want the standard deviation Right? And a lot of times we do want the standard deviation because the standard deviation is intuitive. Right now, variance is in minutes squared. Well, what the heck is minutes squared? Like, how do you interpret minutes squared? So often variance doesn't have units that make sense, right? Minutes squared is nothing to us. But standard deviation comes in the original units, right? We did our measurements in minutes. Standard deviation comes in minutes, and it's far more relatable and easier to analyze. So if we want the standard confidence interval for the standard deviation, we have to take the square root of both sides. Okay. Remember, as we go from variance to standard deviation, we take the square root of the variance to get the standard deviation. Just like when we were calculating variance way back in your first stats class, you first found the variance, did the standard square root to get the standard deviation. There was no direct way to get standard deviation except through the variance. It's the same thing with the confidence intervals. Because this is a confidence interval for variance and a confidence interval for standard deviation. And the calculations are somewhat the same. Right? I find the confidence interval for the variance, take the square root of that, I've got the confidence interval for the standard deviation. Right? Exactly the same as in the calculation, which makes sense. Okay? Do all the inferences, and then I can check to see, okay, has there been an improvement? Okay? If there's been an improvement, I look for 4.25 in that interval. 4.5 in that interval. So for the variance, the lower bound to be 10.488. For the variance, for the upper bound, 36.772. And then I square root each one of those. And now I get the variance is 3.239 and 6.06 minutes. Okay, 4.5 is in that interval, so no evidence to suggest that the standard deviation in wait times has changed here. Okay, so hopefully that all makes sense. Okay, let's roll over to our next example. Okay, so now example number 2, we have a random survey, or random sample of 25 employees at a local utility, showed that their monthly incomes had a standard deviation of $112. Provide a 90% confidence interval estimate for the standard deviation of the incomes for all the firm's employees. Okay, so same kind of idea as we had before. Okay, N is equal to 25. Standard deviation S is equal to 112, and we want a 90% confidence interval, so alpha is equal to 0.10. Alpha over 2 equals to 0.05, and 1 minus alpha over 2 equals to 0.95. All those items that we need as we plug in our particular formula. Degrees of freedom, n minus 1, is 25 minus 1, which is 24. Okay, so first step, let's start to plug in what we do know and then look up what we don't know. So n, which is 25 minus 1 times by 112 squared, and so that's common numerator for both. Uncontroversial. Now the denominator is now we'll look up each one of our chi-squared test statistics. Okay. So we could we'll do this like we've done so far in sort of in the normal course of things. We'll look at the tables and then we'll look up in the Excel. Okay, so let's go back to the table, and we have our degrees of freedom of 24. So I go with the row with 24. Right, my first one is alpha is 0.95. Okay, so I go to 24, 0.95, going across there, and I get 13.848. Okay, 13.848. Okay, I keep on going for 0.05, and I get down to, there it is, 36.415. And that'll be on the lower number, 36.415. Okay. So that's for the variance. I'm going to square root both of those because it's explicitly asking us for the standard deviation. Okay, alternatively, we can use Excel again. Right? Now, kind of neat, we have the left tail, which we have 5%. We have 5%. 5% in the left tail, so 0.05. And right tail, we have 5% in the right tail as well, 5. And there you go, we got our 13.848, our 36.415, same as what we had before. Okay. And so when we bring this all together, we're essentially looking at a confidence interval, $90.90 on the lower end, and about $147 on the upper end. Okay. And like I've commented before, in the inferences we can use that confidence interval for same as what we did for the confidence interval for the mean. Could the standard deviation be $100? Yeah, it could be because it falls in the interval. Is the standard deviation likely to be $150? No. Right, because it falls outside the interval, and so we would be 90% confidence that the standard deviation is not $150. Right? So same kind of idea in the inference here. Right? Again, real easy to miss the square root part of the calculation. Remember, these are confidence intervals. Formulas are for the variance. We square root them to get the confidence interval for the standard deviation. Right? That's real easy to miss. Okay, let's go on to another example here. So let's test for the variance, and the testing structure follows a similar pattern as what we've already established in our hypothesis testing for the means, right? We can have our HO is that the variance is equal to some number. The variance HO is the variance is greater than or equal to some number. HO, the variance is less than or equal to some number, and HA, as before, is exactly the opposite, right? If HO is that the population variance is equal to a particular number, then HA is that it's not equal to that particular number, and so on. In step 3, we have that test statistic, and that's a chi-square test statistic. Follows the same format as we had discussed it in the previous part, or previous unit. It's just that now when we start thinking, well, what could the population variance be? We don't know what it is. We're proposing what it is in our HO and in our HA, and so sigma 0 squared becomes, it's just a placeholder for a particular value that we're wondering if this could be the value. And that's just step 3. Other than that, 6 steps to a statistical test, like there always is 6 steps to a statistical test, and that never changes. Okay. Let's go look at a problem here. Just pretend you don't see step 1 there. So Bob, the grumpy guy, going through airport security. Like everybody going through airport security is always so happy, right? Claims. Claims is an important word to us. Claims suggests that what we're about to read is HO. Okay, standards, claims, those kinds of words that suggest that this is sort of the status quo, suggest to us that HO is coming up. Okay. But there's been no reduction in the variability of wait times at Edmonton International Airports as described in example 1. Conduct an appropriate test assuming a level of significance of 1%. Okay, so step 1, as always, it's our hypothesis. We have our HO, we have our HA. We're talking about population variance, even though standard deviation makes most sense to us. And now the claim has been no reduction. No reduction. So we started off at 4.5 minutes as the standard deviation. No reduction means it stays at 4.5 minutes, or it got worse. More variable. greater tthan 4.5 minutes, right? So greater than equal to, and I'm just going to call it 4.5 minutes squared, just because there's no need to express it to go what's 4.5 times 4.5 and have a number in there that has limited context. This way I can look at that 4.5 squared, I can relate it to the question and to the data I've gathered, and it's just easier to connect my information on one side with what I'm writing down here. And population variance be the opposite. There has been a reduction, right? So it's less than 4.5 squared. Step 2, what's our alpha? Let's go 0.04. Right. Again, we know the whole sophisticated issue as to determining that alpha. Step 3, there's our test statistics. We have our chi-squared test statistic equals to n minus 1 s squared over sigma squared naught. Right? Sigma squared naught. It's just coming out of our hypothesis. S squared's coming out of our data, as is n. So chi squared equals to, what was our sample? I think we had 36 in our sample at the beginning, and a 4.25 squared over 4.5 squared. And we get our chi-squared statistic 31.22, not to forget the degrees of freedom, which is n minus 1, becomes 35. Okay? Can't have one without the other. Can't even remember where that song is from. Anyway. So we need both of those pieces of information to clearly put that chi-squared test statistic in context. Okay. Step 4. Now we're all set. We're going to run with finding the p-value. Okay, so finding that p-value, and we have a couple of choices for finding that p-value. We can look in the tails. Now this will be a little tricky because HA's got a less than in it. Okay? So what we're trying to find is the probability that we get a chi-squared value less than the one that we just calculated. Okay, 31.22. Okay. So now we're going to go back to our tables. And so we'll do tables, and then we'll do the calculation with Excel as well. Okay, so let's go flip back to some tables here. So degrees of freedom 35. There's the row of 35. We're looking for 31.22. Looking, keep on looking. Ooh, it falls between a couple of numbers here. Which means if I look at the very top, it falls between 0.90 and 0.10. Right? I go to the top, I have the columns where the probabilities live. Right? I have my degrees of freedom of 35. My calculated test statistic of 31.22. It falls between 24.797 and 46.059. Now that is the probability that's greater than 31.22. If I want the probability it's less than, I go 1 minus each one of those bounds. Now this is where it gets a little bit hazy and tricky, and that when I go 1 minus, I get that the p-value is still going to be less between 0.9 and 0.10. So it's nuanced, I guess, and it can be a little bit tricky to wrap your head around. Okay, it just happens to be when I go 1 minus the 0.9, I get the 0.1. When I go 1 minus the 0.1, I get the 0.9, and I end up back where I started. Now, does that mean that the greater than and the less than are the same? Absolutely not. As we saw when we were doing the t-distribution, t-inf gave us a t-stat, t-dist gives us a probability, and boom, right? We're able to get exact values without a lot of the anguish of looking it up in a table. Okay, so we could do the same thing with the chi-squared distribution. So we had chi-inf, which when we were using finding confidence intervals, that was very important to us. Right? Chi-inf, gave us the the two chi-squared statistics, so we can do our confidence interval. Chi-dist will do the same for us here. So we have chi-squared. And now we see we have two choices here. Chi-squared dot dist, chi-squared dot dist, and chi-squared dot dist dot rt, right? Now, when we look at our particular question here, our HA is less than. That's left-hand tail, which is exactly what chi-squared dist is going to return to us, the left-hand tail. If we were finding greater than 4.5 squared, we would use the chi-squared dot dist dot rt for right-hand tail. So close that up. What's our test statistic? We punch in 31.22. Degrees of freedom is 35. Always a cumulative probability when given the choice. And 1. Boom! 0.34545. Notice I'm now revealing this because I screwed up clip earlier and I didn't like it. I sounded like a garbled mess. But I still have all the answers correct. I just made no sense. Okay, so that nice, easy peasy, right? Now, on our tables, gives us chi-squared on the right-hand tail. So chi-squared dot dist dot rt. And if we were to punch in the same numbers, right, degrees of freedom, 35, close the bracket, we get 0.65, right? Now, when we were talking about earlier that really confusing thing to wrap your head around is I had greater than is between, the p would be between 0.1 and 0.9. If I do less than, I go 1 minus it, I get 0.1 and 0.9 again. How can that be so? Well, now we see how that can be so, right? Because the probability that chi-squared is less than 31.22 is almost 0.35. Probability that it's greater than 31.2, 0.65. Both of those numbers are indeed between 0.1 and 0.9. And so we sacrifice a bit to get using the tables. Excel gives us a much cleaner answer. But sometimes the tables are all we have to work with, and so we live with that. Nevertheless, regardless of which number that we're looking at, let's kill the wrong one. Which one we're looking at, still a very, very big p-value. And with that very, very big p-value, too risky rejecting H0 in this case, so we will not do so. And so we do not reject H0 with the alpha of 0.04, just too much risk associated with that. Type 1 error would be larger than with which we are comfortable. We're only comfortable with committing a type 1 error 4% of the time. If we were to reject H0 here, we would be committing a type 1 error almost 35% of the time. Way too risky for us. What does that mean? Essentially means no reduction. So we can conclude that there has been no reduction in the standard deviation of wait times. Grumpy Bob, might be right. Okay. So again, we can conclude that there has not been, because we have rejected HA, and we can conclude that there's not been a reduction in the standard deviation of wait times. Okay. All right. All those questions, and just so you know, in the slides, I have the old legacy commands that one used to use. It used to only give you the right-hand tail, and then with the more recent updates in Excel, you can now get the right tail and or the left tail, depending on the situation. So it's made itself a little easier that way, and that's been kind of a nice improvement. But I have the old one just in case somebody's working with an old version of Excel, and then the current one, which we've been discussing here. Okay, one last question, and then we're all settled out on this particular unit. So if any machine should fill to a mean level of 17 ounces, the variance is too large, the filling process is said to be out of control. Standards call for the standard deviation to be at most 0.9 ounces. Okay, so when we see that word standards, that's suggesting that HO is happening here. We're going to see HO in the question, and that's what we do see. When it says at most 0.9 ounces, Well, it could be 0.9 ounces. It could be less than 0.9 ounces, right? Standard deviation could be 0.9 ounces, and it could be less than 0.9 ounces, which suggests an equal sign in this particular hypothesis. And the only hypothesis that can have an equal sign is HO, right? HA doesn't get an equality sign. So we see HO there. So step one, when we're testing our hypothesis, we have HO, we have HA. HO is that the population variance is at most, so less than or equal to 0.9 squared. Remember, the 0.9 is standard deviation. Okay? And then HA is exactly the opposite, greater than 0.9 squared. Step 2, alpha. So it tells us here we want to test a hypothesis regarding the variance if a sample of 71 fills produced a standard deviation of 1.42 ounces at the 5% level. Should the process be discontinued while adjustments are being made? Okay, so we'll make adjustments when that standard deviation gets out of whack. Okay, so if we were to reject H0 in this case, that would mean it was out of whack, and we would have to do adjustments. Okay. So 5% level, so it's telling us alpha is 0.05. And then I move on to step 3, good old test statistic. Got my chi-squared equals to n minus 1 times by s squared all over sigma squared naught. Remember that sigma squared naught coming right out of our hypothesis. Okay. Chi-squared equals to our sample size, 71 minus 1. 1.42 squared all over 0.9 squared. Okay. And we get a really big value of 174.26. Huge. Degrees of freedom is 70, as is usually the case, and minus 1 for us in this particular test situation. Step 4. Okay. Our p-value is we want the probability we get a chi-square test statistic greater than, right? Remember the sign in HA, greater than 174.26. That is going to be a small number, right? It's a very small number. So small that it's not going to be on our table. So let's bring in our Excel sheet. So it's right tail. Okay, so we don't want that one. That one's a left tail. So right tail equals to chi squared dot dist dot RT for right tail. Okay, 174.26 with a degrees of freedom of 70. And oh my goodness, that is a small number. So the p-value, 7.33 times by 10 to the minus 11. That is a lot of zeros. If we were looking on a table, we'd say that is close to 0. But note, we would never say it's exactly 0, because it's not exactly 0, but it's close to 0. That's a lot of zeros before we even hit the first 7. Okay. Nevertheless, step 5, that is one small itty-bitty little p-value. So p less than or equal to alpha. Therefore, we reject that H0. Begone, H0, you are out of here. With an alpha of 0.05. And step 6, this is kind of the old crap moment. We can conclude that standard deviation is greater than 0.9. And what does that mean? What does that mean? The process is out of control. And should be discontinued, right? Feel free to play back the sound. because my handwriting is basically in code. So what it says is we can conclude that the standard deviation is greater than 0.9, because remember we've accepted HA. The process is out of control and should be discontinued. By out of control, it means that it is not, whenever because we've rejected HO, which means the variance in the field is too large, and so the process is out of control by definition. So engineering or instrumentation would have set that guidance for us. And so we can conclude that the standard deviation is greater than 0.9, and whenever it's greater than that 0.9, the process is out of control and should be discontinued.